On this occasion I would like to discuss a rule commonly used in the oil and gas industry, especially in lifting activities. Usually, the oil and gas industry uses DNV-GL-STN001 as lifting standard. It is hoped that with this discussion, you can practice all the rules in DNV-GL when doing a lifting analysis or making a lifting plan. When we do the lifting, we hope that this activity does not have accidents or fail, and for that, we must anticipate by increasing the safety value. The first factor is the weight contingency factor. The second factor is the dynamic amplification factor, otherwise called DAF. So, this DAF is used to anticipate the increasing of the load due to dynamic effects, caused by the movement of the vessel, then also crane movement, as well as swings due to wind. So when in this lifting it's not static, it will move and swing. Now we anticipate it using this DAF factor. Here is the table given by DNV-GL. There are 3 lifting areas: onshore, inshore, and offshore. For example, if we lift a 50-ton object in the onshore area, we use a DAF value of 1.1. But if it is lifted in an offshore area, for example, 50 tons, put in this number in this formula, we enter 50 as SHL. And we get a DAF factor of 1.35, which we should implement. Then, there is another factor called the center of gravity factor, so it means like this. We don't actually know the exact location of the center of gravity. Let's say, COG based on our calculations are here. But actually the reality is here. Now, this shift will certainly cause additional moments, that will put an additional load on the sling here, especially here. This will be heavier. This additional load on sling is anticipated by giving the COG factor. When we create a weight control report, there is Class A, Class B, and Class C. If it is Class A, we are very concerned about changes in COG for lifting operations. But if it's B, we might only focus on the load control, but not consider the COG. For Class C, it applies to projects where the requirements for weight and COG are not very critical. So for A, Class A is critical weight and COG is critical. In Class D, the weight is critical, but the COG is not too critical. Class C, weight and COG are both not critical. Now if, for example, the weight control report is very critical, the accuracy must be high, and we use the COG factor 1.5, but for B and C, because it is not very accurate, then we use COG factor 1.1. Well, this is also in DNV regulated if, for example, we do not use COG factors which are 1.05 and 1.1. We can also consider changes in COG on the envelope whose values are 5% length, 5% width, and 5% height. If our structure is L in length and B in width, then the envelope area is 0.05 L and 0.05 D in length. So when you use this envelope system, it means you have to consider the sling tension that occurs when the hook point is here. COG 1, 2, 3, 4. Well, this is for example, We use the COG1. This means that this hook point is here. This means COG1 is here. COG1, well, up here. It means that the sling is in a position like this later. And later you count the all sling load. Well, then you also later in COG2, the sling load will be here, in position. Then you will also calculate the sling load when the COG is here, above its COG3. Then in COG4, there is also a calculation of the condition of the sling tension when COG in COG4, sling 1 is the maximum. It will be maximum when the position of COG1, sling 2 will be maximum when the position of COG2, sling 3 will be maximum when COG3 and sling 4 will be maximum at COG4. Of these four maximums, which one is the largest, and that is what will be used to determine the sling. The illustration is about like that. The next load factor is the skew load factor. If we are going to lift an object using one hook and four slings, then the distribution of loading on the diagonal slings, this, this and this, or this and this, there is a possibility that the distribution is not 50 to 50. It could be that the distribution is 5/8. And the other side gets 3/8. So if we look here, the first distribution is half, and then we consider it gets 5/8. Of course, we have to multiply by 5/4 or 1.25. This is what is meant by skew load factor. Well, look at it. Look at it all. There are various types of skew load factor. The most common one is used 1.25. Assuming the loading distribution, one sling gets 5/8 portion, and another sling gets 3/8 portion. Look at it. Skew load factor is considered because of the problem of inaccuracy when manufacturing. For example, because of the rigging length. It could be because grommet measurement tolerance around the pin. Then also the rigging length is not accurate according to the calculation. It could also be because of the sling grommet elongation. It can also be crane hook geometry. The next factor is the yaw factor. Yes, we use this factor to anticipate the occurrence of rotation in the vertical axis when the object is lifted. This will also certainly make the sling tension increase. We give the value 1.05. Then the next factor is the tilt factor. The tilt factor is applied if the object is lifted using two cranes. So when this object is routinely used using two cranes, of course, we cannot guarantee that the position of the object is horizontal. There is a slope, and in DNVGL Street 001, the slope is allowed up to 2%. Now there are two ways to apply this tilt factor. The first, we calculate the sling load when the condition is tilted by 2%, or we directly multiply it by 1.03. Another factor is the consequence factor. Consequence factor is used for objects or parts that are directly connected to the lifting point. So the first value is 1.3 that we apply to parts that are directly related to the lifting point, for example such as pad eye, or to the structure where the pad eye is located. This I illustrate, So first the consequences of that factor we apply 1.3 to parts that are connected to the lifting point. For example, we have one structure to be lifted. This beam in this red part, we must multiply by 1.3, while the other part, this one, which is not connected to pad I, is set this. Then we multiply by 1.15.